Right, so looking at example number 6, I'm actually going to skip this one. It's pretty much the same things we've been doing. The exponents are the same. This one would require the AC method, which is going to take just even longer. But we do the same things here with all these critical values. I want to make sure we get through ones that are not equal and then ones that have slant asymptotes. So I'm going to do these examples for starting with number 8 till the end. Alright, so again, the first parts are still the same thing. So we still look at the constants for the y-intercept. That's big. I need a smaller one. So here we have -4 and -2. -4 over -2 is just 2. So then our y-intercept is at 0, 2. So that's where we're going to put our little dot here, 0, 2. Now notice that horizontal this time, the degree, so if we look at degrees first, the degree of the numerator is 1, because it doesn't have a linear equation, it has a degree of 1. And the denominator is squared, so there's 2. So this time the numerator is less than the denominator. So we don't look at the coefficients in front here. We got to look back at our previous page. So I don't have it written here, but we're looking back at the page that had all the points on it. So here, when the numerator is less than the denominator, we said the horizontal asymptote is 0. So that's what we're going to put here. We actually don't have to solve anything. We just say that it's 0 because the numerator is less than the denominator. So y equal to 0 is just the x-axis. So the horizontal asymptote this time is the x-axis. Alright, and then we get into our factored form to get the other critical values. So the numerator is already linear, so I'm just going to leave that as x minus 4. The denominator, though, I want to factor using basic. So -2, I know it's got to be 1 and 2. For it to be a positive 1, I need the 2 to be positive and this one to be negative. So this time, looking at the common factors, so what's common between the top and the bottom? This time we have none. So if there's none, you just put none, because it doesn't always have to have each of these critical values. So there's no holes. That means anything that's left in the denominator is an a vertical asymptote. So this factor equal to 0 is a vertical asymptote at +1, and this factor equal to 0 is another vertical one at -2. So this one actually has 2 vertical asymptotes. One is at 1, so put a dashed line at 1. Can't do vertical lines very well in this thing. And we have 1 at -2. So this graph, this is where it's starting to look weird. So it's not going to look like a hyperbola this time. Alright, and then the x-intercept is still where the graph, or where the numerator is equal to 0. So the numerator equal to 0 is x minus 4. So that means it's at +4, 0. So x-intercept is at +4, 0. So here's where it gets a little tricky because I thought the horizontal asymptote was the x-axis. How can I have a point there? The horizontal asymptote does not mean that it can't be that. It just means what does it get close to in the ends. So in the ends, it's going to get close to this line. It's okay if it touches it around here, but towards the end, you want it to approach it. So looking at this information, that's not a very useful one to figure out what the graph looks like. This is where we definitely need the calculator. So going back to Desmos, so let me take the other example off. So this is the one we're looking at now. So in the middle, it has this parabola looking shape, this U shape. And then at the ends, it has these branches. So again, it crosses here. It crosses, but then it gets closer to it again. It's going to get closer to it. So we go back and kind of sketch the rest of this. So here, we said in the middle, it kind of has this U-looking shape. Right there, something like that. Doesn't cross the verticals. And then over here, it looked like it had a branch on this side. And here, on this side, it crossed it, but then it came back to it. I don't need these graphs to be perfect. Actually, I don't have you graph any of them. You just have to be able to use the graph to match it with its information. Okay, the asymptotes usually give it away, but if the asymptotes don't give it away, then you need the intercepts. Alright, so if we look at number 9, this time they're actually starting us with the other form. So this time we start with factored form. Let's go ahead and see what we can get from factored form. So first of all, are there any wholes looking at factored form? We have a +5 and a +5. So that means we have a whole at, so this is a common one, at -5. So -5 here. Now the y, again, we take -5 and we plug it into the x's that are left. So it's going to be 6 times 5 plus 2. Sorry, -5, because it's opposite, sorry. -5 plus 2 over -5 minus 3, -5 plus 3. So 6 times -5 plus 2 is -3 over -5 minus 3 is -8. -5 plus 3 is -2. So we get, write it over here, -18 over +16. And this reduces, so dividing them both by 2, reduces to -9 over 8. So that means we have an open circle at -5 and just a little below 1. That's like -1 1/8. So -1 and just a little bit below it. Open circle there. Okay, so now from what's left over, we get the verticals by looking at the denominator equal to 0. So here we're going to have one for this one at +3 and one for this one at -3. So draw your dashed lines at -3 here and +3 over here. And x-intercepts, whatever's left over in the numerator, equal to 0. So again, we don't care about the 6 in the front because that one really doesn't give us anything in any difference. So we just want the factor part. X plus 2, so -2, 0. Is your x-intercept, closed dot there. And to get the last 2, we need to multiply it out. Now you actually don't have to multiply it with the whole. You can just multiply, once you cancel it out, you can multiply what's left. So here I'm going to get 6x plus 12 over x plus 3x minus 3. I mean, you can come over here to the side and FOIL it out, but this is a difference of squares. So difference of squares plus minus, I know came from difference of the 2 squares. So x squared minus 3 squared is 9. But if you need to work it out, you can work it out to the side. Okay, so from here, y-intercept are the constants. So the ratio of the constants is going to be 12 over -9. 12 over -9 reduces to negative. Divide them both by 3. Divided by 3 is 4. Divided by 3 is 3. So 0, -4 over 3. And then we do the the horizontal asymptotes by looking at the degrees. So which color am I on? So here we look at the degree of the numerator, and that's 1. The degree of the denominator is 2. So since the numerator is less than the denominator, again my asymptote is going to be 0. So you have a horizontal line at 0. Again, it's okay if it crosses the horizontal. This just tells us what it approaches in the end. Oops, I forgot to do the Y-intercept. So where's the Y-intercept here? Alright, so the Y-intercept is going to be at negative 1 1/3. So just below it there. So that's all the critical values. Now again, we don't have a very good looking graph here. We know part of it's going to be over here somewhere, part of it's going to be in the middle. I don't know about this part. In pre-cal, you'll kind of learn a little bit more about symmetry, but for us, this is good enough. So we just go to our Desmos. So this is the last one. This is one we're looking at now. So it has this branch over here, and then it has kind of like a squiggly in the middle, kind of like a cubic, and then it has one up there. So using this, again, I won't expect you to graph these without a calculator, but you should be able to at least like identify these critical values without a calculator. So here, this part goes like this, jumps over this point, it stays inside this area. This one squiggled kind of downward. And then what was the other one? It's in the top corner, right? Yeah. So in the top corner, we just have this other little piece. So again, I don't need you to have exact points over here. You just need to be able to identify the critical values and kind of sketch it out. Alright, so the last few examples. So we talked about what happens when the exponents are equal and when the degrees are equal. We talked about these when they're less than. The last few examples are when the numerator is greater than the denominator. So that's these last few. Alright, so this is the page where the numerator is greater than the denominator. So notice all the functions above had a horizontal asymptote, whether it was 0 or the ratio of the leading coefficients. However, if there's no horizontal asymptote, then the graph might have what's called a slant asymptote. Instead of it being flat, it has a slant to it. And you'll also see the word oblique. So that just means it's a diagonal asymptote. A rational function has a slant asymptote if the degree of the numerator is 1 more than the denominator. Okay, if it's 2 more, then it's a parabola. If it's 3 more, it's a cubic. For it to be a slant line, it's only 1 degree more. So here I'm going to say the numerator is greater than the denominator, and it's by 1. So the numerator equals the denominator degree plus 1. So if it's not plus 1, it has a different kind of asymptote. It's just not a slant. Okay, but you find it the same way. I'm just not going to ask you to do that. Okay, so looking here at example 10. And so we still got to get all the other critical values, but now we're finding the slant asymptote as well. So let's do the factored form first. Let's get both forms, and then we can fill out this information, and the slant asymptote will be the new part that we find. Okay, so this is standard form. We need to come over here and do factored form to the numerator. So the numerator is going to factor into x. So negative 15, so plus minus. To get 15, I need a positive and a negative. The bigger one's positive, so 5 and 3. And the denominator stays x plus 3 because that's already linear. So if you notice here, I have a minus 3 and then a plus 3. These are not the same factor. So are there any common ones? Nope. So we say none. So nothing cancels out. You're going to put none there. I mean, a lot of these can have none as well. Okay, so verticals is what's left in the denominator. So the denominator equal to 0 would be -3 for the 0 there. X-intercepts is what's left in the numerator when you set that equal to 0. So here we have two things in the numerator, so this one equal to 0 would be a -5. And then this one equal to 0, I have to make another blank here, would be a +3. So these are your two x-intercepts because there's two factors left in the numerator. Now for the y-intercept, we look at the standard form over here, and we look at the constants. So the constant are -15 and 3. -15 over 3 is -5. So 0, -5 for that one. Okay, so all that's review. That's what we've been doing. This is the new part. So for this last part, for the horizontal asymptote, you look at the degrees first. So the degree of the numerator is 2. The degree of the denominator, since it's linear, is 1. So when the numerator is greater than the denominator, this thing has no horizontal asymptote. So the asymptote is none, horizontal. However, because it's one more, it does have a slant. And the way we get the slant asymptote is we divide. So there's two ways we learned how to divide last semester. We can either do long division or we can do synthetic. Remember, synthetic only works in certain cases. So for this one, because it's a linear on the bottom, I'm going to go ahead and use synthetic. But if it's not linear, then you have to use long division. So we'll get to review both of them here. Alright, so let's review synthetic. So we're going to divide. So remember, in the corner is the opposite of your 0. So you're going to put a -3 here for the denominator. That's what you're dividing by. And then you put the coefficients of the numerator. So it's the squared one, the x, and then your constant. So the coefficient of the squared is 1. Coefficient of the linear is 2. And the constant term is -15. So if y'all remember the steps, the first step is to drop the number, 1, and then you multiply diagonally. So -3 times 1 is -3, but then you add these together. So then we get -1 here. Multiply again, -3 times -1 is +3. Add these together, and we get -12. So remember, these go down a degree. So this one ends up being x. This is your constant, and this is your remainder. So we write it as x minus 1 plus the remainder would be -12 over the original denominator, x plus 3. However, for the slant, it only needs the whole part. It doesn't need the remainder. So the answer to the slant asymptote is just this part, x minus 1. So this is, and we'll graph a slant one on the next page. This is what your slant asymptote ends up being. It's the whole part, not the remainder, when you do your division, either long division or synthetic division. Okay, so that's only when it's 1 degree more do you have a slant. You can still do this, but it's not going to be a slant. You're going to end up with a quadratic or a cubic or some other polynomial. This is linear. So a linear line is a straight line that's slanted. Okay, so that's what we're going to do for these last few examples. Alright, so again, we have numerator greater than the denominator. So we're going to have a slant in the end, but let's find all the other critical values first. For the numerator, the first thing we want to do before we factor, or basic or difference of squares or whatever happens to be, is to take out the GCF. So this one has a GCF of x. So if I take an x out of both, I'm going to be left with x squared here and a minus 16. Because originally we wouldn't be able to use difference of squares because it's not a square. This is cubed. But now that we took an x away, now we can use difference of squares. And it's plus minus. Square root of x squared is x and x. Square root of 16 is 4 and 4. Okay, and then the denominator, negative 6 to get negative 1. So negative 6 is going to be 2 and 3, with the bigger one being negative. So negative 3, positive 2. Okay, so once again, what do we have in common between the numerator and the denominator? Here we have nothing in common. So again, there are no wholes. So that means we have a lot of these other ones. So for verticals, that's the denominator equal to 0. So we're going to have 2 vertical asymptotes. So for this factor, it's going to be negative 2. For this factor, it's going to be positive 3. For x-intercepts, the numerator equal to 0. And here, a couple of them, we usually get correct, the parenthesis one. So for this one, we have a negative 4, 0. For this one, we have a positive 4, 0. But this time, that x in the front is its own 0. So when is x going to be equal to 0? Well, when x is 0. So 0, 0 is also an x-intercept. So you got to be careful when x is by itself, because that is its own intercept. However, if you don't get it here, you're going to get it over here anyways. So for y-intercepts, that's the constants. What is the constant in the numerator? Well, it doesn't have one. So if it doesn't have one, it's like a 0 there. So you do 0 divided by negative 6. 0 divided by anything is 0. But notice, if you didn't get it over here, you would get it over here anyways. So either way, you get 0, 0. But 0, 0 is both an x and a y-intercept. Okay, but now we look at the degrees. So the degree of the numerator is 3, and the degree of the denominator is 2. So since the numerator degree is greater than the denominator, the horizontal asymptote is none. So we have no horizontal. However, since it's 1 degree more, we do have a slant. So slant here means when the numerator is the denominator plus 1. So 2 plus 1 is 3. This time, since we have a cubic and a quadratic, we cannot use synthetic division. We have to use long division for this one because it's squared. It doesn't work with quadratics, it only works with linears. So we set up x squared minus x minus 6 divided by x cubed. Now we do need a squared term, so we're going to do 0x squared. This is the linear term, negative 16x, and there is no constant, so plus 0. Okay, so anytime it's missing the number, you gotta fill them in with zeros. So now you ask, x squared times what is going to give me x cubed? X squared times x is x cubed. So then we just take the x and distribute it to all these out here. So x times x squared is x cubed. X times negative x is negative x squared. And this is why you need that 0, so that they line up. X times negative 6 is negative 6x. Now don't forget, when you subtract, that you're going to change the signs to all of these. So this is going to become a minus. You're going to add here and add here. And then you just combine your like terms by adding them together. So these cancel out. And you're left with 0 plus 1x squared is just 1x squared. Negative 16 plus 6 is negative 10x. And then we'll go ahead and bring down that 0. Right, so you're always going to be able to do two steps here. One to get the x term, and then the other one to get the constant term. Because it's always some kind of y equals mx plus b. So the slant is always a y equals mx plus b. So this is the x part. Now we need the b part. So you go one more time. X squared times what is going to give me x squared? Well, just 1. So you multiply 1 by everything. 1x squared, negative x, negative 6. And then you're going to add. So negative, positive, positive. Here we're going to get negative 9x and a plus 6. So this is the remainder. I really don't care about this part because technically we would put it over here, that over this. But for us, we only care about this part. So once you get this number, you're done. X plus 1 is your slant asymptote. You really don't need the remainder. Okay. So the last two examples, I might not do both of them. I just do one of them. Pretty much the same thing. They're just, now they include the graphs. So these last two examples, we're going to need to graph them if we do both. Alright, so I think with this example, we should be good enough with all the critical values for graphing general rationals. Let's go ahead and get these in factored form. So if I factor the numerator, this one has a GCF of x, so I can take an x out of both, and I'm left with x plus 2. Looking at the denominator, it's not a quadratic, so I don't do basic, I don't do AC, but it does have a GCF. And because I want x by itself, I'm actually going to divide both of these by the negative 4, so that x is positive. So this divided by negative 4 is just x. 8 divided by negative 4 is negative 2 here. Okay, so are there any holes? Is there anything in common that cancels out? Nope, this is a positive, that's a negative, so these don't cancel, so there's none. Vertical asymptotes are the numbers that make the denominator equal to 0. So here, this factor equals 0 when x is positive 2. That one we know. But this one over here, when is negative 4 equal to 0? It doesn't have an x, so this is never going to be true. So this one actually doesn't give us a 0. The negative 4 is just a coefficient that's being multiplied. This one doesn't give us another vertical asymptote. Only if there's an x is it a vertical asymptote, or a 0, or whatever it happens to be. Okay, x-intercepts for the numerator. So numerator equal to 0. For this factor, we get a negative 2, 0. And again, the x is by itself, so that is its own 0 at 0, 0. Oh, I forgot to plot it. Okay, so negative 2 zeros here, 0 zeros here. And we have our vertical asymptote at 2. So positive 2 is going to be a vertical line here. Alright, so for the y-intercept, we look at the constants. So what's the constant in the numerator? So there is no constant, so that's like a 0. 0 divided by 8 is still 0. So that's the same point here. Alright, and then what about our slant, or our horizontal asymptote? So here first you look at the degrees. The degree of the numerator is 2 squared. The degree of the denominator is 1. So since the numerator is greater than the denominator, there is no horizontal. However, since it's exactly 1 more, there is a slant. So that's what it says down here, but I'm going to do the work over here to the side. So for the slant asymptote, we have to do division. I'm going to do long division here because the denominator has a coefficient. You could set up synthetic, but that one we actually hadn't learned how to do when there's a coefficient in front. So I'm just going to set it up negative 4x plus 8 divided into x squared plus 2x plus 0. Okay, so you ask negative 4x times what is going to give me 1x squared. Well, I know x and x makes x squared, but negative 4 times what is 1? Well, I need it to be a fraction. I need it to be negative, so it makes it a positive. So negative 1/4 x. Negative and negative makes positive 1, or positive 1/4 times 4 is 1. So positive 1. So now you distribute the 1/4 to the 8. Negative 1/4 times 8 is negative 2. And it's going to have an x. So then I subtract these. So I'm going to subtract the first one and end up adding the second one. So here these cancel out. And I end up with 4x plus 0 comes down. So for this one, what do I have to multiply negative 4 by to get positive 4? Well, I have to multiply it by a negative 1. Negative 1 times negative 4 is positive 4x. Negative 1 times 8 is negative 8. So again, when you subtract the first one, you're going to end up adding the second one. So here my remainder is 8. But I really don't care about that. This is my slant asymptote. So my slant asymptote is y equals m. It's going to be negative 1/4 x plus b is minus 1. So over here, you graph this just like you do a regular line. So you start at negative 1, and you go down 1 over 4. Down 1 over 1, 2, 3, 4. Or up 1, back 4. Up 1, back 4. And you connect it with a dashed line. So notice here this time, the asymptote is slanted instead of it being horizontal. So again, that's the part you have to be able to do without a calculator. To get the rest of it, you go to Desmos, or you get your graphing calculator, and you just graph it to see what the rest of it looks like. So coming over here. So over here in Desmos, this is our other one. This is the one we're looking at now. So notice here, it's a slanted line. So we're going to have, it looks kind of like a hyperbola, but it's not exactly. So we have one like backwards L shape on this side, like a J, and then we have one down here. So going back to our graph, we can see how that works with our graph. We have kind of like a J shape in the top right or top left corner up here. So it starts over here and it goes something like this, hitting that point. I think I missed it. So it starts here, doesn't touch that asymptote, and goes this way. And then the other piece was down here, starts there, and goes down this way. So again, it's very similar to the other ones. You just happen to have a slanted line instead of a horizontal line. So if you just look at the last one, we're not going to go through it all because it's pretty much the same idea. But if you look at the numbers, so this one actually starts you in factored form. But I know that the numerator is greater than the denominator because in the numerator I have 1, 2, 3 x's. So I know it's going to be an x cubed. In the denominator I have 2 x's, so it's an x squared. So I know it's not going to have a horizontal. It is going to have a slant though. So going over here to Desmos, this is what that last one looks like. So again, weird stuff in the middle, but in the end, you have that slanted line right there. For the one we did, you can actually, in Desmos, you can graph the slant, and you'll see that it kind of gets closer to it. So the slant asymptote was y equals m, was negative 1/4 x, and then the b was negative 1. So you can see how it gets closer and closer to that line as you get further, as you zoom out. Up close, maybe not exactly, but as you zoom out, because the end behavior, it does get closer and closer to it. Okay, so that's it for general rationals. You need to be able to identify the critical values, how you get them in the forms. You don't have to be able to graph them yourself, but you should be able to match them. If I give you a graph, like 4 of them, you should be able to match the one that goes with the equation. All right.